because of I will show how to do it in Simbeor. So first we identify the diameter of stitching and diameter of antipod. So for instance, if I go to MATLAB and put those formulas in MATLAB here and define, okay, I need a VF of 45 ohm. Distance between stitching vias is going to be like 16 mil, 8 mil diameter, and run it. It gives me antipod diameter 30 mil and distance to stitching via 34 mil. So those are my starting number for design of via for dielectric constants 3 and any stack up via. So I create solution first, and in this solution, well, it's skip solution configurator. I will use just simple strip stack up with one layer in the middle, like 20 mil layer in the middle. Three decay is 3, dielectric is high quality or low loss dielectric 0.01. This is my starting point. So in I also have to configure the signal. I put it PAM4, 112 gigabit per second, and I'll put moderate rise time, like 15 picosecond. So it reduced my bandwidth to 83 at the spectrum cutoff frequency minus 25 dB. So essentially, this is my simulation bandwidth. Next, I use V-analyzer and create a single multi-via. First, I will start from via barrel. Those top and bottom layer are planes. No back drilling. Pad stack, I'll use smaller. I use in my script 8 mil diameter of drill diameter. The antipod diameter was, just check, 30 mil. No pads on top and bottom. This is the middle section. So I put the same number 8 here. Stitching vias, circle, it's my simple formula gives me diameter 34 mil. So I put 34 mil. This is just starting point. I'll be able to either optimize or adjust it. And again, drill diameter 8, pad diameter 8, and the number of 6. And we can see, don't pay attention to this curve. We are going to improve this model. We basically came up with a new algorithm for this. We will rely on electromagnetic analysis. But this green line is important. It's localized up to 90 gigahertz, which is really good. For this 112, this is sufficient. For 224, you need to go higher. So closer stitching vias or more stitching vias. So ports on top and bottom, via port to, I can use as a via port to, I will use via port to virtual reference plane, de-embedded. This is really important item, de-embedded. Port to ball diameter 1, and I know what it is, but if you don't know what it is, you'll see it in 3D. So if you make any adjustment here and do not know what it is, you should look at on 3D view of the via. Again, I put de-embedded, I put 1 ratio to pad diameter, and what else? In a tuning, because of I created for 45 ohm, I put 45 ohm here. In 3D model, I may need to increase the accuracy. I will keep it at 4 right here because of to run it faster right now. But for final design, I'll put it to like 6, 8. It will run slower, but and this number of cells per wavelength, I could put it up to 100 for high accuracy. So that's it. I create this section and it looks like this. I create 3D model and plot the results. It will create a graph for me, graph 1, where I'll put some dB magnitude for row element, insertion loss and return loss, and adjust simulation options. I need a couple of options to accelerate it and to have TDR at the same time. I switch to algorithm, build rational compact model, compute TD response matrix, save it as default. I will not need to adjust it anymore. So what it constructed is this geometry here. Essentially, this is central part of V going through just one dielectric layer. And one more thing, I need to fill this area here and here with the same dielectric. And this is, so far, it's, when I said manual process, the steps like this, basically, we're going to automate them and make them easier to do. So I put this dielectric in there and hit run the analysis and simulate. And we'll see immediately the graph of the reflection here, and we can create also graph for TDR, just to see how it looks like. Time domain response matrix, impedance here, finish, and on right here we basically see that reflection is -12 all the way up to 80 something gigahertz. Normalization frequency, normalization impedance 45, and if we put it on TDR, we'll see what is the problem. So we put one element just to see. It's the V is a little bit capacitive. You can see it goes dips down here. So because of the planes and because of the formula, actually approximate formula. So to improve it, what do we need? Well, we need to increase the diameter to stitching vias and put it 40 and increase the size of antipod. You can run optimization, but this is just 5 mil adjustment back and forth. So we've got a little bit adjustment here. Localization frequency dropped a little. We create another model that will already have adjusted parameters and click finish and run the analysis. F7, I use F7 to run the analysis, and we'll see how this performs. And basically, that's how you construct the middle section. And you can see this is considerably better. So essentially, right here, we've got a little bit capacitive. Right here, we've got it more or less optimal. Will it stay like this? And I put this graph on TDR as well, diagonal elements. And this is a little bit up, inductive. So it's somewhere in between. There is absolutely optimal case. So now, if will it stay like this when you add number of layers? So make like 10-layer board. Let's just copy the whole project. I copy, paste it here. Paste. Okay. And I'll start adding layers here, like this plane one. I will add a number of plane layers and put 5 mil thickness for dielectric and put some dielectric layers between the plane layers. And I use Control V, Control C, Control V to do this. So we've got now we've got our via going through multiple stack up layers. So it's the same via, multi-via one, which there are two cases basically. One is more capacitive and one is more inductive. This is more capacitive and this is more inductive case. And again, I simply run the analysis. Run. Oh, something is not right. Let me just check. Maybe I need to regenerate it. Let me just regenerate this model and verify that everything is plane. Plane 1, plane 2, those are top and bottom side of the via. And everything else looks like this should be circle inputs tuning. Okay, and generate it and run the analysis. Plot the results on graph 1, insertion loss, return loss, and run the simulation. I can check this box and yeah, now it's running. So copy and pasting and adding those layers, it didn't work. So you can see that the return loss stay almost the same as with two planes and even improves here. But this is just by chance, so it's a 0. So we basically achieved created a via that can go through different layers of stack up. And sensitivity of this via to decay changes is 10% change in decay, only 5% change in Z in impedance, or minus 32 dB in return loss. So this is the most sensitive part is sensitivity to diameter of via. And that's why you saw those whiskers, and that's what basically adds a lot of capacitance to via. So you have to basically create it, design it slightly inductive. I don't know how to predict the effect of those whiskers. You cannot extract the dielectric constant as anisotropic because of it's not in dielectric constant. It's in the barrel of the via. And you basically have to ask your manufacturer why they appear those. My guess is that this is because of very fast drilling. They create kind of split the dielectric and then it filled with the metal during the plating part, plating stage. So now let's construct transition. And to construct transition, again, I go to V analyzer, and this is my multi-via one. This goes from top layer to bottom. But now, what if we need a transition to plane 6, for instance, so layer 6. So what I do, I restrict the via size to plane 6 right here. Nothing, no adjustment in pad stack. I need to put some cutouts below, and I use advanced editor to put plane 5, plane 4, put cutouts on plane 5 and plane 4. This is to reduce the capacitance of via. In stitching vias, nothing, so they go through all the layers here. In inputs, I switch at the layer 2 to transmission line. Stitching via patterns should be circle. Okay, it's circle, and right here I adjust the width of the trace to have about 45 ohm impedance, 44, 7 mil. So that's it. That's design of the transition. So it's going to be, this model is not predicting it well. We need again build 3D electromagnetic model, normalized to 45 ohm. I click 3D, and that created this. Oh, I modified the V that I created before. That was unexpected. So I lost my V that goes through. So I'll need to recreate it. Okay, no problem. So I needed to create a copy with this button first to start modifying. So like this, I created to modify it, and then return it to the original state. Plane 1 to plane 2, plane 1 to plane 2, pad stack stitching inputs, and this is via to virtual reference plane with de-embedded, yes, and with 1 pad diameter. So this is going to be my multivia 2. Multivia 1. Let's just run the analysis and see how it performs. And basically in Simbeor, this transition, the model is not highly accurate here. So for high accuracy, you need to reduce the mesh size to make it much more accurate. But right here we just run it and see insertion loss and return loss. And this is multivia 1. This is multivia 1 in project 2. It goes up to 11 minus 11 dB up to 800 gigahertz. So and this one is multivia 1 from project 1. So they're close to here. So let's take a look at TDR of this vertical to horizontal transition. Again, diagonal elements here. You can see it's inductive. Well, naturally. So to make it capacitive, I need to add the pad size at the bottom. That's where the pad is going to be useful. And it is over here, pads. I find the pad that is at the bottom and put the 10 mil, for instance, diameter, and resimulate it. Just run the analysis, F7. So we'll see how it performs with larger pad. You can see that reflection reduced over here, but then it again goes up. It always goes up at high frequencies, and I'll explain why. That's just physics of the whole thing. You can see the return loss, well, down. So we got it a little bit down. So we can either further increase the pad size or increase a little bit width of this section here. Two options. There are no many options in the optimization of the transition. So it's a pad size and this section width. So for instance, we put it 9 mil. And that's going to be probably highly capacitive. I just put it back to something like 8 mil. What I do now, nowadays we can teach the AI to do this. So this is a set of instructions that I follow. If it's inductive, then you can add this. If it's capacitive, you can add that. And only this part matter. No brute force analysis of the whole thing. So it's still inductive. I'll need to add more capacitance to to this transition. But that's actually good enough already. So you can see it below minus 18 dB all the way up to 65 gigahertz. So it can with this cell size here, it essentially you have to increase the accuracy first and then do the other adjustment, very fine tuning basically. So we constructed two multivias here. This one is I lost in the process, but let me just recreate it. Run simulation. Before running simulation, I forgot to do this. Put FR4 into this virtual plane here. That maybe may provide different result. In VIA1, the same thing. I didn't put the dielectric field into this area here. Okay, and so I'll rerun both of them. So first I rerun sections that fits to any kind of middle section of stack up. And second, I rerun the vertical to horizontal, and then I'll basically concatenate those to get the whole transition into. You can see this one is project 1, this one is project 1 as well. This one multivia 2. Yeah, this is even better. And this one, I rerun it too. So that's how we design V. Differential V is pretty much the same way. The difference is there is no kind of starting point on the impedance, and I can show you how to do the impedance evaluation for differential, just to start with the pattern of differential and stitching. Stitching Vs for differential is probably importance number one. How you put them around, and it will define the impedance of this twin ax waveguide. So you can see right here we got reflection below 20, and then it gets up, and it gets up in there up to the point where there is a conversion of TM mode into high order mode. So that's basically brick wall for this size of V. So right here, there are a few slides basically explaining how it all works and how any stack up V works, single-ended differential and so on. But this is a picture of how the transition from horizontal to vertical take place. So we have quasi-TM mode here, and it gets into quasi-TM mode of basically coaxial waveguide, almost coaxial waveguide. So field direction you can see from here, from here to here. So like in coaxial waveguide. But if you go up to higher frequency, in this case 110 gigahertz, the field that gets into in here, it doesn't get the delay here is almost exactly like quarter of wavelengths, and you getting coaxial T11 mode instead of coaxial mode in the coaxial waveguide, and that is a brick wall of the VIA design. So you cannot really overcome it in any way, and this is how it looks like in kind of animation. You can see this power flow just at 50 gigahertz flow smoothly into the transmission line, but right here you can see that power flow back and forth in this area because of it cannot get here. Top portion and bottom, they have opposite phase, and it's perfect reflection. It's reflected either from here if it gets from this way, or reflected from here if it gets from this way. So that's a brick wall of the VIA design. Everything else you can overcome it easily if you put some micro VIA at the bottom of VIA. like this, or there is design like that. This one requires 1 mil trace. This one also can extend the, if you're thinking about 220 and higher, then you have to basically extend via frequency bandwidths up to above 100 gigahertz. And the only way to expand it is with a micro via transition, via to micro via. Oh, this one is exotic, but this one is actually in use. So that will work. And you can see that this green one. Oh, another option is to make all vias smaller. So stack up all those micro vias. So some companies are do this, but that creates a lot of paths on the way. So that's a problem. It will be really highly capacitive. Right here, the via diameter is 4 mil, then you can get up to 120 gigahertz easily. You cannot do this, obviously, and the only way to get it up to 120 is this one. Transition from regular via to micro via and then to coplanar. So, any questions so far?
That's a lot of good information. Yeah,
Exactly.
we've learned a lot so far.
Yes. Well, you can see it's a work in progress. We didn't convert it into kind of tool. We have some items to improve it, further improve it, and improve vAnalyzer, and to make the whole process easier. You saw that I made some mistakes, like didn't fill with dielectric here, so I need a kind of list in front of me to follow exactly the process. As soon as you do this, then chances to make mistakes are much smaller. I can demonstrate also how to create differential just to start with. Like I get into the same first stack up here. This is my differential, or my single-ended, and now I want differential VM. I click differential and do the same adjustment. First, via barrel the same, pad stack 8 mil diameter and 8 mil pad diameter. This is to construct the middle section first. And stitching vias distance 20 mil pitch. Distance to stitching vias, again, I use oblong. 8 stitching vias. This is probably minimum number you can get. You can be successful with those vias. Drill diameter 8, pad diameter 8, and what else? And 40. This is 40 mil, so it's 40 mil pitch. 20 mil pitch total. So inputs, I use via port to virtual reference plane, de-embedded, again, very important. De-embedding we added just recently, well, probably half year ago, specifically to design such vias, actually. And to improve the accuracy in post-layout extraction. I don't know, have you seen how post-layout extraction looks like? Very easy, and you can use all those types of port in post-layout extraction as well. So again, I adjust those couple of parameters, which is ball diameter and here in here. Extended, yes. So, and anti-pad diameter as recommended for substrate integrated waveguides, you have to adjust it to right here to 35 probably. I need to be more specific. Oh, no, it's a distance. 20 and anti-pad diameter right here, 35. So it looks like twin axe waveguide. It should look like twin axe waveguide. And I create a model now, and take a look at the model, how it performs up to 83 gigahertz. Plot results, and I will use another graph for differential, mix mode here, finish, and elements 1, 1 and 2, 1. Simulation options, I'm not going to adjust them. Oh, before running the simulation, again, one more step is put the FR4 fill on the top and bottom. And right here, every port or I/O is de-embedded to the plane level. You can see those arrows here. That's the idea. So essentially put some ports, de-embed them, and have just middle section. And that's it. Now I can run it, and see differential reflection. So making decision what impedances this via is going to be easy in via analyzer. We obviously working on a model that will predict it much easier. And right here it's minus 16. But impedance is usually smaller, so for such things. So we go to tuning page and set impedance like 85 ohm. And it should automatically adjust it to 85 ohm. Oh, no, it's needed because of I did some changes, so I need to adjust impedance over here. 42.5, something like this. Okay, and this is actual reflection, minus 37. So it's 85 ohm via, almost perfect 85 ohm via. And to make sure that it 85, I can do also one thing. And we almost out of time, but I will show you one step how to simulate it as a transmission line. I created 3D circuit, put a transmission line with 2 I/O up and down, transmission line through, so-called. And into transmission line through, I copy elements of the transmission line created for via. This is T-line Z, and there are a bunch of wires that basically create this via. And unfortunately, we don't have copy paste for the whole group or for the whole multiple elements. So I need to go through 4 of those, 1, 2, 3, 4, 5. Then 5, 6. Just a moment. And then 6 and 4 more. Now use Ctrl-C, Ctrl-V. C, Ctrl-V. So now we've got this, and right here it's an editing mode. So I switch off editor and use D to. This is a transmission line. And the only thing I need to do is, again, we need to improve it. Put FR4 filling. And now we fill with FR4. I can reduce the simulation area here just to run simulation faster and run the analysis. And reuse the simulation from the other. Run the analysis F7. And plot the results as transmission line. So transmission line model. And mix mode impedance. Okay. Bring this here. And you can see this is about 87 ohm transmission line. This structure here. So if you need it under BGA, you'll need 12 of those. You can position them more kind of like under BGA. And this thing is a basic element of the any stack-up via, again, for differential case. And for differential case, the transition is also you will have the same brick wall at a little bit lower even frequency because of the transition into this T11 is pretty much the same in differential, but because of the whole pattern is wider, so it takes place at slightly lower frequency. So this brick wall is unavoidable. You cannot overcome it without reducing the size or reducing the size of this transition. So and then you don't have many options, not many variables to play with. Right here, it's just you create a 100-ohm transmission line, and then you have only path diameter and size of the trace that gets into this path. So you can reduce it or increase it and play with this and see. It usually works at low frequencies, and then you get into this model transition area. So